Swayam Prabha. Digital India. Educated India.
Okay, so SB equals minus 5 is a breakaway point, right? So that's what we have done. So that's why it breaks away, and anyway it goes along the asymptotes, right? But anyway we will come and plot it as we go along, right? Okay, so what is step 5? So we will go step by step, right? So step 5 was to get the angle of departure or angle of arrival, right? But it does not apply here, right? Because why? There are no complex open loop poles or complex open loop zeros here, right? So step 5 does not apply, right, for this problem, right? So let's look at step 6. So step 6 is about getting the crossover points. So for the determination of the crossover points, please note that you need to have look at the closed loop characteristic equation, right? So what is the closed loop characteristic equation? It's going to be 1 plus g of s h of s equals 0, right? So that's what we need to look at. So that's going to be in this particular case 1 plus 2 kp divided by s times s plus 10. Okay, so we are going to get s squared plus 10s plus 2 kp is equal to 0. Here what we do, we are looking for solutions of the form s equals j omega, right? Because that's a crossover point, right? Crossover point is some point on the imaginary axis where a root locus branch may cross from the left of plane to the right of plane or vice versa. Okay, so that's a crossover point, right? So we substitute s equals j omega. So what do we get? We get minus omega squared plus j times 10 omega plus 2 kp is equal to 0. So this will give us 2 kp minus omega squared, that's the real part, plus j times 10 omega equals 0, right? So this immediately implies that from the imaginary part omega is equal to 0 is the only possibility, that means the origin, right? And but already we know that the open loop pole is at the origin, right? So you from the, if omega is 0, that's what we get from the imaginary part, you immediately see that the real part will give us kp is equal to 0, correct? See, 2 kp minus omega squared is equal to 0, you substitute omega equals 0, what will you get? 2 kp is equal to 0, or in other words kp should be 0, okay? So omega equals 0, kp equals 0 is the only crossover point. That means that the root locus does not cross the imaginary axis except when it starts at the open loop pole, that's it, okay? So that's what we can interpret from this calculation, okay? So there are no further crossover points, okay? So it starts at the origin when k is 0, when k tends to 0, because that's an open loop pole, right? So for any kp greater than 0, so the conclusion we can draw is that for all kp greater than 0, the root locus does not cross the j omega axis. Okay, so that's the interpretation we can have. Okay, yes.
So if 0 does not lie on the root locus, then can we directly say that there won't be any crossover point?
0 does not lie on the root locus.
Second step, we are deciding which part of the real axis lies on the root locus. So if 0 does not lie on the root locus, then the j omega axis.
Yes, absolutely. But we need to be careful, right? So okay, I got your question. So I think we might have discussed this point, because you are right. If 0 does not lie on the root locus from step number 2, we can straight away say that the origin is not a crossover point, but I can have a complex conjugate crossover point once again. See, imagine this, like we can have 2 branches which are cutting the imaginary axis. In fact, which happened, if you recall, last week, right? We considered another example where we had open loop poles at plus or minus j. It was not a crossover point, but the 2 branches started on the imaginary axis. You are correct, but what I am adding to your statement is that that only says that 0 is not a crossover point. It does not exclude the fact that we can have crossover points on the imaginary axis. Okay? Right. Okay, so let's go back and complete the root locus. So what's going to happen is that, like, we are going to have 2 branches starting from one starting from minus 10, one starting from 0. They break away at minus 5 and then they just go to infinity along the asymptotes. Okay, so that's what is going to happen. Okay, so now the question is, for what values of Kp, this is the root locus, right? We have plotted the root locus. So now you can see the advantage of using this method, right? So we have a visual characterization, right, or a visualization of the 2 branches of the closed loop poles, right? So 2 branches of the root locus, each one corresponding to 1 closed loop pole, right? So you can immediately see that for all Kp greater than 0, both branches lie in the left of plane. So as we already know, Kp greater than 0 implies closed loop stability. Now we want closed loop performance, right? So the question is, for what range of Kp would both branches lie in that open trapezoidal region, right? That's the question we need to ask ourselves. So how can I determine that? See, where is the open trapezoidal region? Let me redraw it, highlight it in green once again. So it is this, right? So for what values of Kp would the 2 branches lie within this region? How do I find it? First, I need to find the value of Kp at minus 2, right? Because one branch of the root locus starts from 0, keeps on increasing, keeps on coming to the left as Kp keeps on increasing, and it comes within this performance region only when it crosses minus 2, right? S equals minus 2, right? So how do I find the value of Kp at S equals minus 2? Obviously, I substitute S equals minus 2 in the closed loop characteristic equation. What is the closed loop characteristic equation? It is this. So if you substitute S equals minus 2 here, what do you get for Kp? Kp should be 8, right? You substitute S equals minus 2, right? So what we are going to do is that so consider the closed loop characteristic equation, right? S square plus 10s plus 2 Kp is equal to 0. Okay, so here if you substitute S equals minus 2, we get Kp to be 8. Alright, so that's pretty straightforward algebra, correct? So Kp is going to be 8 here. So now you can see what we have done, right? For stability, we wanted Kp to be greater than 0, right? For performance, Kp should be greater than 8, right? Only then both branches will enter into this trapezoid. But not only that, we have to find out what is the value of Kp when the root locus hits this point and this point, right? Because beyond this, the 2 branches of the root locus go outside the desired region, right? So how can I find the value of Kp at this point? First I need to figure out, like what is that point, right? How do I find out the coordinates of that point? I hope it's clear what I am doing, right? I am figuring out for what range of Kp would the two branches of root locus lie in this green, what to say, the region, open trapezoidal region, which is bounded by this green colored lines, right? So how do I calculate this point of point? I can use the angle, right? So can you tell me what is the coordinate? Of course, it's going to be real part is minus 5. What is going to be the imaginary part? Yeah, what's that going to be? 5 tan 53.76, right? So what do you think you will get? So what is this value? And similarly, what is this value? What is 5 times tan of 53.76? Please take tan 53.76 multiplied by 5. What do you get? 6.82. Okay. So this is going to be j times 6.82 and this is going to be minus j times 6.82. Now how do you find the value of k at that point or Kp at that point? Once again we substitute the corresponding value of S in the closed loop characteristic equation, right? Right? See, what is the value of S here? Minus 5 plus 6.82j. Please plug it into closed loop characteristic equation. If you do that, please check it. I got the answer as 35.76. Okay, so that's what I got the answer as. Okay, so if you substitute it in that closed loop characteristic equation, okay, 35.76. So what does this imply? This implies that for performance I need to essentially have my proportional gain to be between 8 and 35.76. That's it. Right? So what I can conclude is that for satisfying closed loop stability and performance, okay, Kp should be in the region 8 and 35.76. Okay. So please note that, see, initially to begin with Kp was a real number, right, between minus infinity to plus infinity. Stability essentially reduce that region into half, okay, only from 0 to infinity. But that's once again a big region, right? So through this analysis, what we have done, we have figured out that, look, 0 to infinity will give me closed loop stability, but then 8 to 35.6 will give me performance also, the way I desire it, right? So don't you think this is a very useful tool to know? So please note that what we have done, we have progressively reduced a huge region of proportional gain, minus infinity to plus infinity, first we reduced to 0 to infinity. Then 0 to infinity now has been reduced to 8 to 35.76, right? And even if I go back to the root locus and look at this, in fact, I would design for some Kp between 12.5 and 35.76, right? Because by and large, we would want our closed loop system or control systems to be slightly underdamped, right? So if I want to satisfy the performance specifications and closed loop stability and still design an underdamped second order system, right, I would choose Kp between 12.5 and 35.76. I can also choose Kp between 8 and 12.5. That will also satisfy performance specification, but the system will be overdamped. See, if you have an overdamped system, where is maximum peak overshoot? So maximum peak overshoot anyway is not there, right? And yet I can satisfy the condition on settling time, right? So that is essentially this one. Of course, it's going to be slightly sluggish, right? Because the settling time expression assume that like you are going to have an underdamped second order system. So in a certain sense, like what I would do is that like I would pick Kp between 12.5 and 35.76, okay? So that it's consistent with whatever analysis we have done. Because please remember, how did we get the desired region of closed loop poles to begin with? By using the step response of an underdamped second order system, right? For an underdamped second order systems, the poles should be complex conjugates, right? When are the poles complex conjugates as per the root locus here? When Kp is greater than 12.5, right? So I would choose Kp between 12.5 and 35.76 and tune the final system, okay? So this way the analysis, theoretical analysis can help us figure out a range of controller gains. Then we need to go to the actual experimental system and fine tune, okay? So that's what ultimately we would end up doing, okay? Is it clear? Yeah, because why is 12.5 the transition point, right? Because please note that the two branches of the root locus are starting from minus 10 and 0, right? And when Kp increases from 0, you can immediately see what's happening, right? So one branch is going to come on this real axis, right, in this manner. Another branch is going to start from 0 and travel to the left, okay? So what do these branches indicate? They are the closed loop poles. So till Kp equals 12.5, you can immediately see that both branches are on the real axis. So then what can you say about the closed loop poles? They are real. If you have two real distinct poles for a second order system, what is it called? Overdamped, right? So at 12.5 they intersect, they become critically damped. And then beyond 12.5, you see that the two branches go into the, move away from the real axis. So you have complex conjugate closed loop poles, right? So the system becomes underdamped, okay? Yeah.
Now I know I can calculate this mathematically. Is there a logical explanation for why Kp is negative 35. So Kp is again 35.76 in the lower.
Okay, because we are dealing with a symmetric root locus, right? So because if you are going to have what to say, two closed loop poles, like at the same value of Kp, think about it this way, right? Kp is a parameter, right? So let's say you substitute Kp equals 35.76, you are going to have one closed loop characteristic equation, right? You are going to have some constants as parameters. So when you calculate the roots, since we are dealing with real that is polynomials with real coefficients, if you have a complex root, the conjugate also must be a root. So conversely, if you parameterize the polynomial using one parameter, you choose any two complex conjugate roots which are solutions to that polynomial, the value of the parameter should be the same, right? Otherwise there will be a dichotomy, right? Is it not? Okay, that's why Kp is the same, right? So it doesn't matter whether it's minus 5 plus 6.82j or minus 5 minus 6.82j, okay? Yeah. Fine. So I hope it's clear, right? So what we have done is that like we have just ran through one study where we can generate models and do this process, right. So, of control design, right. So, that is just to give a flavor of what we could do with whatever we are learned. And you can immediately see that root locus is a very handy tool to know, right, because like you can have a graphical visualization. See, if I had asked you, like without a root locus, how do you satisfy these conditions, performance conditions, it would have been very difficult, right. It would have been more challenging to get these bounds, right, on KP. With root locus, it was quite straightforward and also very intuitive, right, because we can see the graphical visualization, right. Okay. So, what I am going to leave you is a homework problem where this is just for your own learning process, right. So, plot the root locus for the same system, okay, when Kp is negative. So, this is just an exercise for you, so that like you get familiar with the other ways of plotting the root locus also. So, you immediately, obviously you will see that when Kp is negative, already we know that like closed loop system is not going to be stable. You will see that one branch will always go in the right of plane, okay. So, that is what will happen when Kp is negative. But the reason I am asking you to do it is because, see, many times people would want the root locus to be plotted for a parameter that is varied from minus infinity to plus infinity. Then you can't essentially plot at one go. What you need to do is that if you give me a transfer function like this and you ask me to plot the root locus for Kp going from minus infinity to plus infinity, right, because why, what was the open loop transfer function? It was 2 Kp divided by s times s plus 10, okay. Now you ask me plot the root locus, for Kp, for all real values of Kp, right. So, I need to go from minus infinity to plus infinity, right. So, what I do is that I divide that region into two subregions, minus infinity to 0, 0 to infinity. Then I plot the root locus for one region, let us say minus infinity to 0, that means Kp is negative, and then 0 to infinity, that means Kp is positive. Then I get the complete root locus, okay. So, that is what I want you to do, right. We have plotted the root locus for Kp greater than 0. As homework, what I want you to do is I want you to plot the root locus for Kp less than 0, so that you get the complete picture. Obviously, you will realize that the closed loop system is not going to be stable for Kp less than 0, right. So, we will just confirm that or support that result, like using the root locus, fine. So, please do this. So, this completes our discussion on root locus. So, what we are going to do is that like from the next class, I am just going to go to frequency response, but before we go to frequency response, in the next class I am going to give you a brief introduction to what is called as the state space representation, right, which forms the basis of what is called as Borden control theory, which you will learn maybe as a next course in controls if you chose to go into control systems, okay. And in fact, we will use those tools also in advanced controls courses, okay, like whichever courses you take, right, on advanced controls. So, I will just introduce that to you and show you the equivalence between the two approaches, but this course is going to be about transfer function, right. But since we are at the halfway point, I thought that is a good time to introduce state space to you, right. Then we will go to what is called as frequency response analysis. We will do frequency response, that is a response of this class of systems to sinusoidal inputs. We will study those characteristics, and then we will learn how to analyze systems for the frequency response, and then like design controllers using frequency response, okay. So, that is going to be the second half of our course, fine, okay. So, I will stop here and then like we will meet on Monday. Thank you.